torque and angular momentum in terms of moment of inertia. Moment of inertia I to be related with torque and J. Torque or moment of a force, both are the same. For a rotating body, torque is given as the product of the movement of forces acting on all the particles. Many particles. Forces are acting on them separately, F1, F2. Their distances perpendicular are R1, R2. So this would be given as, and F1, is M1, A1, R1, M2, A2, R2, then M1, A is equal to R alpha, this is R1 alpha, R1, R2 alpha, R2, and so on. This becomes M1 R1 square, M2 R2 square into alpha, that's I alpha. I alpha, you got the relation for torque in terms of moment of inertia, that's directly given here I alpha. Similarly, you might say that J, angular momentum, is the product of momentum of all the particles. Product of momentum and its perpendicular distance. Or you might say it is the momentum of all the particles. You proceed this way, you just convert P1 by M1, V1 and so on. This thing, it will be R1 omega, R1, R2 omega, R2, M1 R1 square, M2 R2 square into omega. Again, you see omega is common to all because angular velocity, angular acceleration for a rotating body is same for all the particles. This becomes I omega. You find J equal to I omega. Two relations you are having for tau and J. Like for force and P. For P you have mv, for force you have ma. So mass is exactly in place of I or vice versa. That means I is rotational analog of mass in rotational motion. Now let's review the relation for tau and J. You know, tau is delta J upon delta T. If tau is 0, see, tau delta T, this is delta J. This would be called angular impulse, the product of torque and time interval. But if tau external is 0, this will be 0. Delta J would be equal to 0. Delta J stands for change in angular momentum. If some quantity is not changing, obviously that's going to be constant. You relate these two, you get one very important law of mechanics, classical mechanics. What is that? Angular momentum shall remain conserved if there is no external torque. If external torque is not there on a system, its angular momentum will remain conserved. This law itself is very important. Since you know J is equal to I omega, this will be constant. You might say I1 omega 1, that is equal to I2 omega 2. On this basis, we conclude that when moment of inertia will increase, omega will decrease, or vice versa. If you want to increase angular velocity, obviously you have to decrease the moment of inertia. Divers keep this thing in the mind. While in the air, divers always try to just contract the shape. They try to reduce their shape, their size. What happens? Angular velocity increases. That helps them other way. Similarly, you might have heard the name of neutron star. Neutron star is the possibility of one of the conversions after the death of a star. You know, when stars die, they are likely to be converted either in white dwarf or in black hole or in neutron star. Neutron star is one of them. But the size becomes so small that the speed becomes very, very fast. Neutron stars are supposed to spin very fast. They are known, in fact, for their speed itself. And finally, I have quoted that angular momentum conservation has many applications. Angular momentum itself is a very significant quantity in mechanics. This law has wide application in Kepler's second law as well.